Welcome back to the lab. This video was supposed to be about testing the boost converter in our UPS. Oh, joke's on me, we blew it up! Dang it! So where did we leave off? I was just testing our first UPS board. Well, I tested our UPS until it wouldn't power on anymore, so I guess we were done testing our first UPS board. By the time we were done, the power input of the UPS is shorted to ground, 2 of our inverter FETs exploded, and the hot swap controller is way too sensitive. Our 50 amp current limiting is tripping at less than 6 amps. What? This might seem like a lot of issues, but by the time we're done today, we'll hopefully have found the root causes or a few probable causes for these issues. And once we find out what caused these failures, or what likely caused these failures, we'll make some plans for a couple of reworks that we can use to get these boards back in working order. If we planned our PCB well, we should be able to solve our problems with a few straightforward mods, and hopefully there won't be too much jumping and cutting involved on our PCB. Hopefully we can keep things minimal. Now, since I'm one person, the very first step in this and any troubleshooting exercise needs to be prioritization. I can only have one first priority, so what is the first problem we should give our focus to? What problem is the most critical? In this case, all of our issues are a pretty high priority, but transistors blasting themselves into bits and the power ground short seem the most critical to me. In fact, we can't do any testing on physical hardware until we get this board powered on again. So let's start with that DC power input short to ground. I guess we'll need to start our investigation in the design files then? So we can't start on the board, so yeah. Let's dive into the power ground short by looking at the schematic first. Let's trace out the power path through the inverter. Let's start at that DC power input and walk through the pages of our schematic until we find something that looks a little fishy. After we narrow the fault down to a couple components, we'll start removing parts from the board until the fault is resolved, and there you go. We'll know what part caused the short. All right. So what's connected to this DC power input anyways? There's a couple fuses, reverse polarity protection diodes, and that's about it. Pretty confident that our low voltage off-the-shelf regulators aren't going to be an issue here. Those are all fused independently, and if they were pushing this much current through them, those fuses would blow. So no concerns on this page. Next comes the relays and the hot swap controller. So a short from the relays to ground is incredibly unlikely, borderline impossible. The hot swap controller is a pretty similar story. We're performing high side switching. Ground isn't really involved in the power path except for as a part of the power supply for the controller itself. But this would need to have a short to like the gate drive, and then I just don't see this happening. This means the issue probably isn't in this circuit either. Moving on. This is where we get to the push-pull converter, and actually this might be the end of the road. The issue should be somewhere in this circuit, because this is the last circuit directly connected to the nets where we're seeing the short. Everything downstream of here is powered by the output of this push-pull converter, but that's across an isolation barrier, so there's nothing that could cause a DC short. Okay, so probably not the controller, same deal as before, but I wonder if it could be those NMOS FETs, the PSMN 016 FETs. I wonder if the controller could be latching those FETs on, or if we've damaged the FETs in such a way that could cause them to fail short. We did see a different misbehavior from this controller. 2 failure modes come to mind for a transistor fault itself: excessive gate drive voltage that would cause it to permanently be stuck on, and violating the drain to source voltage rating of the FETs. I think that either of those overstresses would probably be capable of producing an enhancement NMOS FET that's always conducting, or a transistor that's always stuck on, which is what we may be seeing here. Let's follow this train of thought and dive into the gate drive voltage theory. The gates are driven by the transistors that translate open collector outputs from our push-pull controller into a gate drive signal, and those are being sourced by the power input. Okay, so this range varies from 11 to 40 volts, but if memory serves, we're driving this circuit with 24 volts. We might be onto something here, because 40 volts would be, a bit much to put on the gate of a FET. So let's double check the gate voltage rating of the FETs that we selected. Well, there's your problem. Our transistors are rated for 20 volts from gate to source. We were applying 24 up to 40. That's not what you want. Alright, so I need to limit the gate drive voltage to something reasonable. The output transistors are going to be supplying 40 volts, but that doesn't mean that we can't protect the FETs. A resistor divider would be one way of scaling the voltage from 40 down to 11, but in order to drive our transistors on fast enough, we'd need some pretty excessive currents flowing through our gate drive transistors. And those transistors are pretty physically small. Now that I'm thinking of it, the resistors are 2, 0603. I'm guessing just based on physical size alone for these circuits, that they will not be able to handle the kind of power we need. A simple resistor divider, therefore, is not the best solution. What else can we do? Well, we could replace those two 0-ohm resistors with a 90-ohm and a diode. The diode would keep the turn-off time for the FETs pretty close to ideal, but limit the current when turning on. This will impact the efficiency of the supply for sure, but hopefully the effect won't be too excessive. Now that there's a current limit on the gate drive signal, if we replace R69 and R70 with 12-volt Zener diodes, this could really turn into something workable. The Zener will prevent the gate drive voltage from rising too far above 12 volts, but unfortunately that same Zener will likely be the weakest link in this chain. We're limited to something that will fit on 0603 pads, and the fact that we want the gate drive current to be as high as possible means that our input voltage range will be fighting against us. When we optimize the gate drive current for 11 volts, this circuit will be screaming hot when 40 volts is applied. We'll be dropping around 28 volts across that gate drive resistor. Yikes. So what does this mean? If we're willing to give up some gate drive current, we can find an optimal gate drive resistor value. For sure, our transistors will dissipate more power when switching, but our FETs won't blow up, and that's definitely a step in the right direction. Even better, this rework doesn't require cutting any traces. Sounds great. So we'll be increasing the power dissipated on our push-pull converter, and that might not be practical when we crank this thing up to 700 watts, but it should work well enough for some light load testing and general debug tasks while we work through the rest of these issues. This gate drive circuit will prevent our push-pull converter from voltage overstress while we resolve the rest of the problems that we observed. Let's give this a try on our next board and evaluate how well the mod really works for our application. If it doesn't meet our specs, if it doesn't work as well as what we'd like, we can try a more aggressive rework that will fix the problem with a sledgehammer. So look at that. We have one rework planned, and the most probable cause has been identified. We'll find out soon if the root cause that we believe we've identified is truly the root cause after we remove the push-pull transistors, apply this rework, and observe the new behavior. For now, let's move on to the next issue. Let's keep planning. Exploding FETs. So the transistors that we're working on now are a part of the inverter itself. Based on the violence of the explosion, I'd say that, if I had to guess, around 20 joules of energy was dumped into our transistors at a rate of about 400 watts. Sounds about right. That's approximately how much energy we have stored in the output capacitance of our push-pull converter when charged to 500 volts DC. In other words, I'm saying that I think we saw shoot-through here. The catastrophic failure, I believe, was caused by both transistors, the high and the low, conducting at the same time, where in this state, they just absorbed a massive gulp of energy really quickly and caused them to literally blow in half. But the thing that I can't wrap my mind around is why only one? We have two copies of the circuit on the PCB. We drive them identically. The power supply is identical. The drive signals are identical, but one exploded and one didn't. The schematic is an exact copy, so we're not going to find anything there. Let's look into the layout. What could possibly be different in our physical implementation of these two chips? The main thing that I see here is the routed length of the power nets. The two transistors that were undamaged are fed by power supplies that are very physically close to the gate driver, very close to where the voltage regulation occurs. The other gate driver isn't so lucky. There's local bulk and local decoupling, sure, for both of these gate drivers, and they're routed in an identical way, which is good, but bulk and decoupling only gets an IC so far. It's possible that the resistance or inductance of the traces between here and there might have just been too much for our gate driver to function correctly. This fault is strange, since our gate drivers claim to have guaranteed dead time, and we don't appear to be overstressing them in any way, even at 500 volts. But if we're browning out the gate driver in either voltage region, the performance of the IC will become undetermined, so that claim of guaranteed dead time might go out the window. Let's investigate this when we have another working board. I don't see an immediate issue here. We've done a lot of power cycles before we bricked the board, and we never saw this issue again. So we'll investigate that power quality by taking some measurements. We'll zoom in on the ripple of the power supplies near the two gate drivers, probe the power ground nets, and if we see brownouts, dips, if we see any opportunities for improvements or see a risk of violating the rated operating conditions of the gate driver, we'll just have to fix it. Whether we add some additional bulk, run some wires across the board to get cleaner power to that remote gate driver, the one on the far side of the board, we'll do whatever we need to do. Our rework doesn't need to be pretty, but we just simply cannot have our transistors blowing up. We need this thing to work. Whatever we do to benefit the gate driver will probably help out the nearby current monitoring IC2, which could be the weirdness that we are seeing on the analog voltage measurement there. That chip could be browning out as well if it's on the self side. So power integrity could be a factor in this region of the board. Okay. Two issues have some causes that seem to make some sense. One more issue to go. What's going on with this hot swap controller? It's cutting out way too soon. The current shunt resistor networks look correct. It should be set for 50 amps. That said, there isn't really a whole lot of local capacitance for the controller. There just isn't a lot of local capacitance. And I'm not sure if we can really add it. I mean, there's a 0.1 and 100 picofarad decoupling cap nearby, but that's nothing when compared with the current that's flowing through here. I don't know how much we can really do to stabilize VCC. There's only so much we can do. VCC for the hot swap controller is the same as VCC for the whole UPS. That means that it's going to dip right alongside the downstream load, and 50 amps is flowing past this point of the circuit. That means that we need an absolutely ridiculous quantity of bulk capacitance to do anything about VCC stability. So I guess that means we might have found the problem, but we don't have a solution? That doesn't sit right with me. Let's keep investigating. What else could be going on? Well, the programmed current limit might be tripping due to noise, like we were thinking. Well, not quite, but it could be tripping due to noise rather than true overcurrent events. So there's a little flicker of what would be equivalent to 50 amps, even if it was like a steady state 0. Okay, so we can mitigate this by forcing the controller to always measure a 0. By depopulating R85, the hot swap controller will always measure 0 amps. That could work. Another thing we can try is disabling the undervoltage lockout function. When R74 is depopulated, the UVLO threshold will be set to the minimum value, giving us just a few more volts of margin before tripping. Can't completely eliminate the UVLO, but it'll widen the band where it won't trip. If not the UVLO, current sense or power to this part, just scrap the circuit. As we've discussed before, we can offload the hot swap controller's functions to other parts of this design. Sure, it would be nice to have the hot swap controller in the design, no doubt, but I'm really on the fence about keeping it, even if it worked perfectly. The hot swap controller adds a bit more than 15 milliohms of series impedance to our UPS power path. When 50 amps is flowing through the UPS, that would be 38 watts of power dissipation. That's like 5% of our output power. I'm just not sure if I think the hot swap controller is worth that kind of loss. In this application, with the nuisance trips we're seeing, I just don't know. I just don't know if this makes any sense. We'll see. Let's make those couple tweaks to the resistors surrounding the hot swap controller and see how far that gets us. For our immediate testing, we'll also bridge the hot swap controller with a wire. Let's fix the most critical problems before zeroing in on the hot swap controller. After all, there's a clear solution here, and that solution is a wire. Most of all, let's remember these reworks by writing them down before we forget, and we'll test out our theories when we build the next UPS. Oh boy, I'd really love to get in the lab. I would love to start implementing these changes and testing out the reworks, but unfortunately serial number 1, this first board, is probably going to need to be replaced with serial number 2 for this test. We've applied about 1.5 times the rated voltage we designed the components on the high voltage side for. 2 of our inverter FETs catastrophically failed, but the other 2 might have suffered some latent damage as well. It just might not be as obvious of a failure. The push-pull converter is broken. We've racked up quite the number of broken parts on this board. We've racked up enough failures that well, I don't want to put another $50, $75 worth of components into a board if something else is broken. I'd rather start our next round of testing with fixes in place on a new board that's known to be good. I'd rather be testing on some known good hardware and making measurements that we can trust and pick up our analysis from there. There's just too many unknowns with this first board, with the state of serial number 1 right now. We'll keep this board as a spare for sure. We're not going to throw it out. But let's wind another transformer, build another board, and do this right. Testing too many variables all at the same time is a really bad thing. There's just too many opportunities to arrive at misleading conclusions when you can't trust the hardware. So I guess this means we'll see you in 5 days, huh? Do you think we can get all this built? Do you think we can get ready for this next video? I certainly hope so. This UPS project is really coming together. If you like what you're seeing today, then subscribe to be notified of our future videos, where we'll apply the fixes that we just thought of today while building serial number 2. We'll see if these fixes mitigate all of the issues that we saw while testing serial number 1. I think that we found some great answers to our questions, and if you think so too, then let me know by hitting the like button on this video, chatting with us on Twitter, or leaving a comment letting us know what you enjoyed. Most of all, I hope that you learned something great today, and I hope to see you again soon. So thank you for watching EE for Everyone, and thank you for staying till the end. Bye!